So tonight we're going to be looking at comparing distributions of categorical variables, but we're going to be looking at two-way tables instead of one-way tables. So we will still be using a chi-square test, but we will not be using the chi-square for goodness of fit. So we use the chi-square. This is the one that we did last time. Okay, so in your calculator, the GOF one. And so that one, the chi-square goodness of fit, allows us to look at one-way tables, and we're looking at distribution and comparing that. And so tonight we're going to be looking at the chi-square. So same thing for homogeneity. Oh, I ran out of room. So we're looking at the chi-square for homogeneity. And one of the things that we may need to do for that, okay, is we may need to look at our conditional distributions, our proportions. And so we're going to be using this example kind of all the way through. So in this particular example, we're looking at music, the type of music that's played, and then the entree that's ordered. So we're looking at two different categorical variables here. So I have my two-way table here. And part A for this particular problem has us looking at the conditional distributions of the entrees ordered for each treatment, with each treatment in this case being the type of music. So the first thing, we'll pick a type of music. So let's go with none. So when no music is being played, 30 out of 84 entrees, okay, are French. And so that would give us a 0.357. So that would be our French. So when no music is played for Italian entrees, I have 11 out of 84. So we're just going down this column right here, right? No music. And I'm looking at my proportions for these, 0.131. And then other, so not French or Italian, I get 43 out of 84, or a proportion of 0.512. Okay, so you would go through and you would do this for every type of music and for every entree. So as I continue through here, I would look at, then I would move to the next type of music. So looking at French music, and when French music is played, 39 out of 75 entrees are French. Italian, it's only 1 out of 75 entrees, and other is 35 out of 75 entrees. And so these give us proportions of 0.520, of 0.013, and 0.467. And then I would do that for my final type of music. So for my Italian music here. So when Italian music is playing in the background, we get entrees, French entrees being 30 out of 84, which gives us 0.357. Italian entrees being 19 out of 84, which gives us 0.226. And other entrees being 35 out of 84, which is 0.412. And then you would finally be done with part A. You had calculated the conditional distribution of the entrees ordered for each of the different types of music. So then for part B, it has us making an appropriate graph for comparing the conditional distributions in part A. So an appropriate graph for this would be a bar graph. Okay, and so you can see we have 3 different bar graphs here, one for each explanatory variable, which was our type of music. Right, our type of music was the thing that we could control, so that's our explanatory variable. So we have a graph for each one of those explanatory variables. On the side here, on our y-axis, we have the percent or the proportion there for our entrees, and we have a bar for each type of entree and each type of music that we listen to. So part C on this question has asked us, move this graph off to the side, has asked us to write a few statements comparing the distributions of entrees ordered under the 3 music treatments. So when you're looking for this, basically you're just looking to describe what you see in the data, what's going on there. Okay, so what we see happening here is that we've got definitely have differences across the 3 different music, types. We have differences among the entrees that are ordered. Italian entrees are very, very low when there is no French music. So that when there is French music, excuse me, so that kind of stands out, that we have this very low number here for Italian entrees ordered when French music is playing. Okay, and then the fact that when Italian music plays, those go up a lot more. French entrees seem very popular in general, regardless of the music. The French entrees are always pretty popular and ordered pretty frequently. Okay, but definitely a little bit more when French music is playing. And then the other entrees is pretty similar regardless of music as well. Okay, so that's all you're doing. It's just looking to describe what you see going on here. So since this chi-square for homogeneity is a type of significance test, we're going to have to do a null and alternative hypothesis. So when we're doing our null and our alternative hypothesis here, our null is always going to be that there is no difference in the distribution of a categorical variable for several populations or treatments. So thinking back to the restaurant example here, our treatments were the fact that we had these different musics, right? The different kind of music. So the null hypothesis for this particular experiment or this particular situation here would be that there is no difference in the true distribution of entrees, because that's my responding variable there, to the true distribution of entrees ordered at this restaurant when no music, French accordion music, or Italian string music is played. So I do specifically list the different types of music as well. Okay, but that's my null hypothesis. I've got no difference, basically regardless of which of these 3 types of music that are playing, I have no difference in my true distribution of entrees. Meaning, basically, regardless of, let's say there's no music playing, I should have a third, a third, a third. There's French music playing, a third, a third, a third. Okay, our alternative hypothesis for this chi-square test is going to be that there is a difference in the distribution of a categorical variable for several populations or treatments. So again, in the restaurant here, I've got a difference. So there is a difference in the true distribution. You notice they're using that word true again. In the true distribution of entrees ordered at this restaurant when no music, French accordion, or Italian string music is played. They're using all of that context. Some of you are still shortcutting context, and you can't do that. So to be able to calculate a chi-square test statistic, and be able to actually run the test, we have to know our expected counts. Remember, our formula for chi-square, right, is the sum of the observed minus the expected squared divided by the expected. Remember, we are comparing our observed and our expected numbers. So we need to be able to calculate the expected for all of these. So if we're looking here we've got our two-way table here. And what we've got going on is that 99 of the entrees that were ordered were French. And so what we're going to do here with this information is we're going to look and we're going to see, depending upon the type of music that was played. So for instance, if no music was being played, 84 total entrees were ordered when no music was being played. Okay, and so I know that out of all of the entrees ever ordered, so the 243 entrees, okay, my percentage of French entrees is 99 over 243. Right, that's my percentage of French entrees, which would be basically 41% of all entrees ordered were French. So if on any given night, so on this given night here where I ordered 84 entrees, I would assume that about 41% of them would be French. So I would expect about 41% of them to be French, which means I would expect about 34.22 entrees to be French. And so I can continue to do that for the other types of music. So this is when no music is playing, and I'm looking at French entrees here. And so this is when French music is playing, and I'm looking at French entrees. So again, I expect about 41% of them to be French, because 99 out of the 243 were French. And when French music is being played, there was a total of 75 entrees ordered that evening. And so that would give us a total of 30.56 entrees. And then I can do that for my last one. So when Italian music is playing, and I'm looking at French entrees, 84 entrees were ordered that night as well. And again, I would expect about 41% of them. So again, I would expect to have 34.22 of the entrees be French. So now I have expected numbers for all of the French entrees that were ordered. And you could go through and do the same for the Italian as well as the other. And so I would recommend that y'all go ahead and pause it and see if you can figure those out. And then I'll show you, I'll go ahead and just give you the answers real quick. So hopefully you attempted those. And here is what you should see. Oops, sorry about that. Okay, that when I determine my percentage for Italian entrees, okay, again, I can determine that by getting that 31 of the entrees that were ordered were Italian. So I get my 31 over 243, which gives me a percentage of almost 13%. So then I apply that to my totals, my entree totals for each night. And I expected when there's no music to see 10.72 entrees, Italian entrees. When there was French music, 9.57 entrees and that were Italian, and 10.72 Italian entrees when there was Italian music playing. And so for the last one, your other entrees, you had 113 out of the 243. So that gives you an expected percentage of 46.5%. So again, applying that to my totals entrees that were ordered each night, I expect to see 39.06 entrees ordered that were considered other when there was no music, 34.88 other entrees when there was French music, and 39.06 other entrees when there was Italian music. Okay, you can see here where they have put this into an expected counts table for you. So you may have picked up on it, that you have a formula for finding your expected counts. Okay? Your formula for finding your expected counts is to take that row total, so that 99 for the French ones, times the column total, which would have been the 84, and then dividing that by the table total, which is the 243. Okay, and that will give you that same 34.22 expected French entrees when no music was being played. Okay, so you can use that formula there to find your expected counts. Okay, also when you're doing a significance test, like always, you need to check conditions. So the conditions for your chi-square test for homogeneity is they're the same as always. Okay, the fact that they need to be randomized experiment, or from independent random samples. If you're sampling without replacement, so basically you're not doing an experiment with volunteers in a very specific population, for a very specific population, you have to meet your 10% rule. And your large counts rule is a little bit different here. So my large counts rule, well, it's not different from the last chi-square. all of my expected counts need to be at least 5 for our large counts rule. So, and we met that with all of these entrees. We had the 9 different expected counts that we figured out, and every single one of them was bigger than 5. So this particular example would meet our conditions to be able to go ahead and run the test. So to keep working our way through the test, to actually calculate the chi-square statistic, it's the same formula as we had before, our observed minus expected squared divided by expected. We're just doing this test for a different reason. So your chi-square goodness of fit test is going to be when I have a hypothesized distribution. They're all uniform, there should be the same Fruit Loop percentages for colors. Okay, so when I have a hypothesized distribution for one categorical variable, and I'm checking to see if my data fits, so it's my goodness of fit. Okay, in this one, we're not doing that. So in this one, we are comparing the distribution of categorical variables the same for several populations or treatments. So we're looking at our distribution of a categorical variable from several samples with each other, not comparing it to a hypothesized distribution. So when you calculate this test statistic, you'll see up in the corner here just a reminder of a way that you can calculate that and make sure you're showing your work. Remember, you don't have to show every single calculation. You can put the dots in there. You can show a couple of them, put the dots in there, and then basically let your calculator do everything else. So, for instance, for this one, I figure it's a lot less messy to show it to you this way than to watch me write it. Okay, so for this one, my French entrees with no music, so that'll be my first one. Remember, I have to sum all of these up. So I need to do this for all 9 of these values that I have, right? So I observed, for no music, I observed 30 French entrees, right? I expected 34.22, and so I subtract that, square that, divide that by 34.22. And then for French music and French entrees, I observed 39. I expected 30.56, so I run that one. And now I've shown enough to prove that I know what I'm doing. Okay, I indicate that I would do that for all of them, and I finish with the last one, which is the other entrees with Italian music playing. So I finish with that last one, okay, and I get my final chi-square statistic of 18.28 is my chi-square test statistic for this particular example. So now that I have this test statistic, I need to find out what my p-value is. I need to interpret that. So I'm going to use, for part A on this one, it asks us to use table C, and then it asks us to use the calculator. So we are going to walk through both of those just so you get an idea. So if I'm using table C, I need to know my degrees of freedom. Okay, and so my degrees of freedom, actually I need to know that to do in my calculator as well too. So my degrees of freedom here would be 3 minus 1 times 3 minus 1. Okay, so I have 3 categories of music and I have 3 types of entrees. And so I subtract 1 from each of those and I'm going to multiply that. So I've got 2 times 2 gives me 4. Okay, if you think about your degrees of freedom, we're not going to, at this level, we're not going to be able to truly explain degrees of freedom. But if you kind of think about how this would work, where if I had, let's say I had a table here, and I know the sums of all of these rows, of these values. Like I know what this adds up to. That makes it look like it adds up to 0, so I apologize for that. Okay, so I know the answers for all of what these add up to. I could kind of put whatever I wanted here and here and here. But once I had filled 3 of the spots, this one here is fixed, right? It cannot vary. I don't have any freedom in that one. So I had 4 options, but only 3 of them can vary. Think about with your Fruit Loops, right? You had 6 different options of color, okay? And so those 5 out of 6 can kind of fluctuate and be whatever they want. But once you have those 5 out of 6, that sixth one doesn't have a choice. It has to be what it will be to add up to the total. Okay, so our degree, that's why we subtract 1 from our degrees of freedom. Well, that's the kind of bare bones reason as to why we subtract 1 for our degrees of freedom. So if I'm taking this degrees of freedom in my table C, which I find my 4 degrees of freedom, and I go over until I find where my chi-square test statistic would fall. Remember, my test statistic was 18.28, so it falls here between 16.42 and 18.47, which means I have a p-value between 0.025 and 0.01. So my p-value would be between that. Okay? If I'm doing this in my calculator, then I'm using my chi-square CDF. And so I'll show you where that is. So you've got your chi-square CDF function. So you'll find that under your distribution. So your second vars, where you find your normal CDF, your inverse norm, your inverse T. So you'll go down to number 8, your chi-square CDF. And in your chi-square CDF, you're going to type in your lower value, which is 18.28, your upper value, which is going to be some big giant number, and then 4. So it would look like, let me get rid of this stuff here. So it will look like in your when you write it out, like if you had to write it out and show your work for that, you'd have your chi-square CDF, just like your normal CDF, right? And you'd have your lower, which is 18.28, right? My statistic, my upper, which is the big giant number, and then my degrees of freedom, which are 4. Okay, and when I run that, that should give you a specific p-value of 0.0011. And now that I know that p-value, I can interpret that just like I used to. So let's first look at part B though. So part B has us interpreting that p-value in context, which I think is still kind of an issue for some people. So remember, on that blue inference chart that you were given, okay, it gives you a way to interpret your p-value, right? Remember, the first thing you need to do is you need to assume the null is true. So assuming that the null hypothesis is true, okay, then my p-value is a probability, right? Then there is a 0.0011 probability. I'm not going to write the whole sentence because it's messy. If you want to see the whole sentence, you can go to page 705 in your book. But again, you have the stem for this on the front of your inference chart. So assuming that your null hypothesis is true, there's no difference in the true distribution of entrees ordered in this restaurant when no music, French accordion music, and Italian music is playing. There is a 0.0011 probability of observing a difference in the distributions of entrees ordered among the 3 treatment groups as large or larger, okay, as large or larger than the one in this study. So that would be my p-value in context there. Again, if you want to see the whole sentence, go look at the example, which is on page 705. You won't be able to read it if I write it here. Okay, and then the last part here, we're deciding what conclusion we would draw and we justify our answer. This is the exact same that we have always done as well, okay, which again, you have a stem for this on the front of your inference chart, right? Because the p-value 0.0011 is greater than, or I'm sorry, is less than our alpha equals 0.05 because we weren't given one, so we use our default. We reject the null hypothesis, right? We reject our null hypothesis. Okay, we have convincing evidence of a difference in the true distributions of entrees ordered at this restaurant, when no music, French accordion music, or Italian string music is played. Okay, so, and because the fact that your assignment here was random, it allows you to say that the difference was caused by the music, okay, because this was a random experiment, we'll say. Okay, so let's look at how to do this on your calculator. Okay, pay attention to your tips here about using your calculator. You're welcome to use it. Just make sure that you are going to get some credit, hopefully, on that do step. Okay, it tells you here the best way to get credit is to write out the first few steps to calculate your do your calculation. Okay, and then then go ahead and punch in your number from your calculator. Okay, name what you did on your calculator. Okay, name the fact that you did that. Always give that test statistic, degrees of freedom, and the p-value. And we're going to add to your inference chart, and we're going to kind of make note of what the things are that you need to make sure you need to say. So the first thing you're going to do is you're going to use a matrix here. You guys are probably more familiar with matrices than I am on your calculator. Okay, so you're going to use the matrix, and you're in matrix A, you're going to enter your dimensions, and your dimensions are going to be basically the size of your two-way table, not counting any of your header columns, rows, or totals. Okay, so totals do not factor into the size of the matrix as you are putting together the matrix. Okay, and then you're going to go ahead and you're going to enter your observed counts into the matrix. So the observed counts go in there. Okay, you're going to specify the chi-square test, the matrix where the observed counts are found, and the matrix where the expected counts are to be stored. So now you will press stat, okay, stat test, just like we had before. And this time you're going to choose your chi-square test. Before, for the one categorical variable, remember it was the chi-square GOF. Okay, so this time it's the chi-square test. Okay, you're going to adjust your settings. So you typed your observed into matrix A. You're going to send your expecteds to matrix B. Okay, and then you can choose the calculate or the draw. When I choose the calculate, I get my test statistic, my p-value, my degrees of freedom. All need to write down. You need to write all of these need to be written down. I can't spell. All of those need to be written down to try to get your credit here. If you do the draw, you'll see the chi-square distribution. Remember, they're skewed right, non-negative values with your 4 degrees of freedom. Okay, in the area of the tail where the p-value is will be displayed. We have a very small p-value, so it's probably so you can't really see the very small area that's shaded down there. To see the expected counts, because you'll need to write down your expected numbers to be able to, when you check your conditions, you can't just say that they're all greater than 5. You need to write them down so they know that you actually checked them. And so you can go to that matrix. You can go to matrix B, okay, and you can find your expected counts so that you have those and you can get those written down. Okay, and so you can do all of it on your calculator. You just need to know what you need to write down and what it means and where to find stuff. So we've got another example here where we're going to run through the whole example and not just keep going kind of piece through it. Okay, I'm not going to do a lot of writing. I'm going to kind of just pull the solution pictures in and kind of show you and walk through it to hopefully speed this up a little bit. So the first thing I'm going to tell you is to go ahead and pause it for a second and read the problem so you know what's going on. Okay, so we have 2 parts to this problem. In part A, the first thing it's got us doing is comparing the distributions of political party affiliation for cell-only and landline phone users. In part B, we're doing an alpha 0.05 level test that the distribution of party affiliation differs in the under 30 cell-only and landline user populations. So let's look at part A first. Okay, so for part A, it asked me to compare the distributions of political party affiliation here. Okay, so basically this is what we did in the beginning when we looked at what we have and we're just kind of talking about what we see and what's going on. So because the sample sizes are different, we need to look at proportions. If we had the exact same sample size, it would be more comparing apples to apples. But I can't say that 49 and 47 necessarily are super close together if it's 49 out of 50 versus 47 out of 1,000, right? So we need to look at the proportions here. Okay, and so we would go ahead and calculate our conditional proportions, conditional distributions. And when I calculate those distributions, I get this table here. Okay, and so the table shows us our conditional distributions for the political party affiliations. Okay, and I've got this time it was a segmented bar graph that they made so that they could look at and try to compare these. And so by looking at this information, they stated here that our cell-only users appear slightly more likely to declare themselves as Democrats or Republicans. No lean is right here in the middle. Okay, and so we had a little bit more a little bit higher percentages of cell phone users that were leaning one direction or the other. So basically 84% of cell-only people would pick a party affiliation, whereas 74% of landline users picked a party affiliation. People with landlines seem to be much more likely to say they don't lean Democratic or Republican. And that's really kind of the only thing they could find here because our Republican and Democratic numbers are pretty close together. Okay, so as we move into Part B has us running the significance test. So it's like always, it's a 4-part significance test, right? We have to state, we have to plan, we have to conclude, we have to do. Okay, so the first part here, our statement, okay, it's a significance test. So I need a hypothesis. Okay, so I've got a null hypothesis that I'm going to have no difference in the distribution of party affiliation in the under 30 cell-only and landline populations. Again, I cannot stress all of this context. You can't just say, what I'm seeing a lot is that your hypothesis would say that there is no difference in the distribution of party affiliation. But this is specific. These are people under 30 years old. Okay, and we're looking specifically at whether they're cell only or they're using a landline. Okay, and then so our alternative hypothesis is just going to be that there's a difference. And like always, I need to write my alpha. Okay, my alpha of 0.05. Okay, so from the plan stage, I need to move on, or from the state, I need to move on to the plan stage. So in the plan stage here, I'm going to use a chi-square test for homogeneity. So I need to write that out, which test it is that I'm going to use. Okay, I need to determine that it's a random for both of them, and they were both independent random samples. And I need to note that. I need to note that both of them were independent random samples. I can't just say random checkbox. Okay, 10%. So sampling without replacement was used. Okay, so I've determined that I need to have a population of at least 960 cell phone users under the age of 30, which is a definite, and 1,040 landline users under the age of 30. And it's pretty safe to assume that there's going to be at least 1,040 people that are using a landline still. Okay, and then for large counts, remember with chi-square, our large counts, we need all of our expecteds to be at least 5. You could go through and you could calculate those from the table. To do that, I would need to get a table total, right, which would be 200. But I could go ahead and I would need to get my totals over here as well. But I could go ahead and I could multiply my row total times my column total divided by my table total. Okay, or I could go ahead and I could put this stuff into my calculator. And so if I follow my technology steps and I put it into the matrix matrix A and I run it and I send my expecteds to matrix B, I can get my expected right there, and they are all greater than 5. So I meet my conditions and I can move forward and actually run the test. So to show my work when I'm doing my test statistic, okay, you can go ahead and you can show your first couple, right? Follow your dots, plug in the number from your calculator, which is 3.22, right? I need to write down my p-value, 0.1999, and I need degrees of freedom. Remember, I need the test statistic, so I need the actual chi-square value. I need the degrees of freedom, and I need the p-value. to ensure that I get full credit. My degrees of freedom, right? My number of rows minus 1 times my number of columns minus 1. So 3 minus 1 times 2 minus 1. So 2 times 1 is 2. Okay, and then I can move on now up to my conclusion. So my conclusion for this would be that because our p-value of 0.1999 is greater than my alpha of 0.05, I fail to reject my null hypothesis. I do not have convincing evidence, and then I put in all my context, right? All my context. So occasionally, after you go through and do this, you may be asked to do some follow-up analysis. Do not do follow-up analysis unless it specifically asks you to. Okay, do not do it, again, unless it specifically asks you to. So this goes back to the restaurant example, and this is Minitab software. So this is another example of a kind of software printout that you could see. Your free response portions of your AP test will a lot of times show you data like this from a software simulation output. So in this Minitab software here, okay, you can see where I've got my observed in the first row, right? There's my expected in the second row. So I've got my observed and my expected for each of them in the first and second rows. And then what I have is each of my individual, here's my summary data down here, my chi-square statistic, my degrees of freedom, and my p-value. But what I have as I go through is I have each individual on this data, I have each individual portion of the chi-square statistic, right? That's my observed minus my expected squared and divided by my expected in that very last row. And so if I'm doing follow-up analysis, I'm going to look at these ones right here that kind of stand out, right? And I want to be sure that I'm addressing size and direction when I am doing a follow-up analysis. For instance, the follow-up analysis on this one would be something along the lines of fewer. That would address size and direction, right? Less than, moving towards the negative. So fewer Italian entrees are ordered than expected when French music is playing. Okay? And you see that statistic with this one right here, right? That I have way fewer observed than I expected. My music is along the top here, right? And my Italian entrees. So I have way fewer expected when French music, way fewer observed than expected. Okay, and same, again, you see this large portion of these are the big things that are influencing my statistic, right? I see a large amount over here I see a much larger amount of Italian entrees ordered than I expected when Italian music is playing. So I'm addressing the size and the direction. Again, you would only do that kind of follow-up analysis if you are specifically asked for it. Okay, so we'll do our last chi-square, the second part of 11.2 in our next stuff.